In this tutorial, we're going to take a look at the zeros of a quadratic function and how that relates to the quadratic formula, specifically one part of that, but we'll get to that shortly. So a little note here at the top left-hand corner. If you determine the location of the vertex and whether the parabola opens up or opens down, then you can use that to determine how many x-intercepts, how many places it crosses the x-axis. So we're going to look at four functions here. The first one is as y equals x minus 4 squared minus 3. So the vertex of this would be at 4, negative 3. And since a is 1 here, the step pattern would be just the standard 1, 3, 5. So if we were to plot this, so if we go over to 4 and down to negative 3, and the step pattern is 1, so remember that means you go over 1, you go up 1, left 1, same thing. From each of those, if you go over 1, up you up 1, 2, 3, and the same thing on this side. And I could do the 5 as well, but I won't bother. So that's what that one looks like. And so notice its vertex is below the x-axis and it opens upward, so there are 2 zeros to it. That's what we're focusing on, how many x-intercepts or how many roots or how many zeros there are. So let's look at this 3x plus 7 squared one next. So and I'll put the equations on them. Now if you're drawing this, try to put stuff in the same place that I do, because there's actually going to be 4 graphs on here, so that they don't like one on top of another. Put it up here and it won't interfere with other things. So the 3x plus 7 squared, now remember there's no number added or subtracted on the end, so that means that the y coordinate of the vertex is 0. So it would be at negative 7 comma 0. And there's a 3 here. So remember, for the step pattern, you multiply each of these by 3. So this is going to be 3, this is going to be 9, and 3 times 5 is 15. So that one's got a fairly big step pattern. So the vertex is at negative 7 over here on the x-axis. And so we go up 3 on either side. And then 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that's what this one would look like. Next one, this blue one here, negative x plus 5 squared minus 4. The vertex would be at negative 5, negative 4. Oh, and we'll put our equation on here. Negative 5, negative 4 for this one. So let's plot this one too. So negative 5, negative 4 would be right here. And there's really, the a value is negative 1 here. So the normal step pattern just gets multiplied by negative 1. So it's going to be negative 1, negative 3, negative 5. So there's our vertex. So the negative 1 means we go down 1 instead of up 1. And then down 3 here, something like that. So that's what that one looks like. And I'll talk about zeros more. I'm going to finish the red one here, and then I'll talk about zeros in general. I did mention this one, but we'll get into those in a moment. So this one's in standard form. It's not in vertex form. So we could complete the square. I'm going to try to do a little variety here. So I'm going to find the x-intercepts. I'm going to put it in factored form. So the a value is negative 2 here. So I'm going to factor a negative 2 out of all this, and write my equation. So I'm going to factor a negative 2 out of all this. And then to factor this, we look for two numbers that add to 2 and multiply to negative 3. And those numbers would be negative 1 and positive 3. Those numbers add to 2 and multiply to negative 3, so that's factored form. So the zeros, and so I'm doing this one a little different way than the vertex form. So the zeros would be at, see, if we set x plus 1 to 0, we get 1 for a root. So we'll put a dot there, 1 on the x-axis. And if we set x plus 3 to 0, we get negative 3 for a root. And so if you have the roots, now we could still find where the vertex is if we were doing the completed square. But when you have the roots, this is one of the more convenient ways to find where the vertex is. The axis symmetry is halfway between those, which of course would be here at negative 1. So we'll put a line down through there. So that means, remember, the vertex is on there somewhere. So everywhere on that line, that's the line x equals negative 1. So that means that the vertex is negative 1 comma something. We have to find what that y value would be. And we could find that again by completing the square, but we could also substitute the -1 in place of x in this equation, or this one, wouldn't matter. I'm going to use the standard form one. So I'm going to put -1 here and here. And -1 squared is 1 times -2 is -2, so that's -2 at the beginning. -4 times -1 is 4 plus the 6, so that's 10 minus 2 is 8. So that's the y-coordinate of the vertex. It's at -1, 8. So -1, 8 would be right up here, 6, 7, 8. So that's the vertex. And we could do the step pattern too to graph this. Obviously, we know where these roots are. So if you so for the step pattern, since the a value is -2 here, we multiply the 135 by -2, so -2, -6, -10 would be the step. So from our vertex, we'll go down 2 on either side, and then down 6 takes us to those roots. And I won't bother with the -10, I guess I could do it here, but that's certainly enough to sketch it. So that's what that one looks like. So I talked about this one first. If the vertex is below the x-axis and opens up, well, it has to go through the x-axis twice, 2 places. This one has the vertex above the x-axis and opens down, so again it has to go through the x-axis at 2 places. So those both have 2 roots or 2 zeros or 2 x-intercepts. This one only has 1 because it actually just touches the x-axis, it doesn't cross it. So whenever you have a vertex on the x-axis, you have what's called a double root. The 2 roots are the same, and so there's really only 1 root. If the vertex is below the x-axis and opens down, well, it never is ever going to cross the x-axis. So there are no x-intercepts, no roots, no zeros. And the same would be true, I'll just draw this one. If I had a vertex, let's say up here, and it opened upward like this, like that, then that is also never going to cross the x-axis, so it would also have no zeros whatsoever. So those are the 4 possibilities. Well, actually, these are both the same. There's 3 possibilities here. I wanted to show you 2 of these. So let's flip over, and I'm going to talk about the quadratic formula with each of these, and I want to show one part of it. I'm going to get to that. I'll write in my equation here. So on the next page, I'm going to do the 2 that have the 2 roots first, and we'll get into the purple one and the blue one on the following page. So this is in standard form. So I'm going to use my quadratic formula here. So, and let's fill in the values. So a would be -2, so -2 here and here in the denominator. B is -4, so -4 is 4, and it's -4 we're squaring here. And so maybe I'll bring over my calculator here. So at the beginning here, that's going to be -4 squared will be 16. And then now I'm going to use the sign for the -4, so it'd be -4 times -2 times the 6. So it's going to be 16 plus 48 under here. And of course, 2 times -2 is -4. And so 16 and 48, I add to 64. And the root of 64 is 8. And so we would go 4 plus 8 over -4 and 4 minus 8 over -4. And of course, maybe I'll do these 2 roots on here. So 4 plus 8. Notice I'm using brackets because I want to evaluate the whole 4 plus 8 before I divide it by -4. So that's going to be -3. And then, and nice thing about the graphic calculator is you can just edit this instead of typing the whole thing over again. Now the -1, so -3 and 1. And so those are going to be the 2 roots here for the red one. -3 and 1. And we can verify that from the graph. That's the red one here. See 1 here, -3 here. Those are certainly the 2 roots. Okay, now we're going to do the black one next here, the other one that has 2 roots. So in order to use the quadratic formula, I need to expand out this x minus 4 squared, and it's, well, it looks like this. I'll do it beside the graph here. So x minus 4 squared means x minus 4 times another x minus 4. We're just expanding these together. So x times x is x squared, and then that'll be a minus 4x. That'll be another minus 4x, and negative 4 times negative 4 is 16. So we've got the x squared here. There it is. That's negative 8x, and 16, and then minus 3 is where the 13 comes from. So that's where we get the standard form from. And, okay, so now quadratic formula. So, looks like this. So a is 1 because it's 1x squared, so 1 here and here. B is negative 8, so negative 8 would be positive 8, and negative 8 squared here. And C is 13, so 13 here. So, inside the radical, we're squaring the negative 8. That's going to be 64. And then negative 4 times 1. Don't really need to bother the 1, really. Times 13. So it's going to be 64, take away 52 underneath the root here. And I guess I'll do that subtraction just to show. So it's going to be 12. So 64 minus 52, which of course is 12. So we need to evaluate those. I double-clicked there. I didn't mean to go that fast. Of course, you can pause if I'm going a bit too fast here. So I showed the calculator exercise down here, but so it's 8 plus the square root of 12. I need to close my bracket. That closes the bracket underneath the root, and then the whole top, and then divided by 2. So that's where my 5.73 number comes from. And then I want to do the minus 1, so I'll go back and edit and just change this to a subtraction sign. And that's where the 2.2679, etc. comes from. So that's two calculations, and it looks okay. So it looks okay about 2.3. See, that's 1, that's 2, so 2.3 there. And about 5.7, see, that's 5, that's 6, it's a little bit less than that, so 5.7 seems very reasonable. 2 roots. Now notice the two that have 2 roots, and we'll get into the other 2 in the next page. Those 2 roots happened because the number underneath the root is a positive number. Okay, and I'll be generalizing this after we finish the next 2 quadratics and the following page, but because there's a positive value here, that's why we have 2 different roots. So we'll get into the next page here. So the 3x plus 7 squared, that's this one here. So again, I need to expand out the x plus 7 squared. And so if we expand this out, so x times x squared, x times the 7 is a 7x, and then another 7x here to add to 14x, and 7 times 7 is 49. And then we distribute the 3 in. So 3 times x squared will be 3x squared. 3 times 14x will be 42x, and 3 times 49 is 147. So now we want to use the quadratic formula to find what the 2 roots are. And you can see here that it should just be a single root, the negative 7. So we fill in the values. This one has much bigger numbers than the previous 2. So b is 42, so negative 42 here and 42 squared here. A is 3, so 3 goes here and 3 goes here. 2 times 3 in the denominator. And then 147 is the c value right here. So we might need the calculator for this one. So underneath the root, I'll clear this, we got 42 squared. So that's going to be 1764, and minus, well actually I shouldn't do that, negative 4 times 3 times 147. And look at that. This is going to be 1764 minus 1764. We're actually going to get a 0 underneath the root. And that's one of the things I want to show you in this exercise. So that's 1764. We're subtracting 1764, which of course is 0. So the root of 0 is 0. So there's really no reason for the plus or minus, because plus 0 minus 0 is just the same as not having anything there at all. It's really just negative 42 divided by 6, which is negative 7. So that single root happened because the value underneath the root is 0. That's why that happened. Okay, last one here, the one that has no roots, never goes through the x-axis. Well, what happens to the quadratic formula here? You need to expand out this x plus 5 squared. So 2x plus 5s. And so very similar to what we did over here, x times x is x squared. This product will be a 5x, and this is another 5x to make 10x, and 5 times 5 is 25. And then we collect, we distribute the negative 1 in. So this would be negative x squared minus 10x. And see, this is going to be minus 25. Subtract 4 is negative 29. So that's the standard form of that, or this right here. So now we want to use the quadratic formula. So let's put the next line too. So b is negative 10. So negative 10 is 10. So negative 10 squared here. A is negative 1, so negative 1 here, and negative 1 here. And C is negative 29, so negative 29 here. So let's do this. Okay, so we've got the negative 10 that we're squaring. Of course, that's the same as 10 squared. So that's going to be 100. And so now we've got minus 4 times negative 1 times negative 29. So this is 100. And from that, we're going to be subtracting 116. Remember, there's 3 negatives here, so that's why it's going to be subtracting 116. Now, 100 minus 116 is negative 16. So underneath the root, we get a negative. And now so let's see what happens. We plug negative 16 here. Take the root of negative 16. Oh, look at that, non-real answer. Okay, the calculator doesn't like that because you cannot, in the real numbers, take the square root of a negative value. So there are no real roots here. That's why that one does not cross the x-axis, because the value underneath the root is negative, is below 0. So if you get a 0 here, that's when it gives you the 1 root, but if you get any kind of a negative, it never crossed through the x-axis. There are no x-intercepts to that parabola at all, which happens some of the time. So, little bit of a summary on the next page. I'm going to show you something after this summary before we get into one example. So the number of zeros is determined by the value of the discriminant. If we go back to, actually let's go back for just a second here. This thing here, underneath the root, that's called the discriminant. And discriminant means it discriminates between having no roots, 1 root, or 2 root. That's why it's called the discriminant. It isn't a negative term, because we often think of things like to discriminate as a negative thing, which it certainly is if you're discriminating against someone. But in this context, it just means it chooses between having no roots, 1 root, or 2 roots. So if the value is negative, like the last example, then there are no real roots, there are no zeros, so it looks like this. The vertex is above the x-axis and opens up, or below the x-axis and opens down. There are no real roots. If there's 1 real root, then the value of the discriminant is 0, like the x plus 7 squared one. And it looks like this. There's the vertex on the x-axis somewhere like this, kind of looks like that. And if there's 2 real roots, like either of these, so 1 real root, another one here, or here and here, then the discriminant value is greater than 0. So that's the only possibilities. It's either equal to 0, 1 root, less than 0, no roots, or greater than 0, positive, and there's 2 roots. So before we go into the one example, I want to show you this Geometers sketchpad drawing. So this is a dynamic thing here. This is my general standard form, and I'm going to vary the values for the coefficients A, B, and C. Right now I've got a 2 here, and I've got a negative 2.02 in place of B, and there's no particular reason for these, and negative 3 is the C value. And so if I grab a hold of the slider in the end here, I can make and remember A is the stretch value. See how it's getting less steep? Okay, that's the standard parabola, pretty close to there, because A is exactly 1 there. So see if I start my vertex over 1, up 1, over 1, up 1, 2, 3, over 1, 1, 2, 3, 4, 5. So there's a step pattern. So, and of course, if we make, whoops, I didn't grab a hold of that. The bigger we make it, the steeper it is. So there's a value of about 9, so it's pretty steep. And of course, if we make a negative, it flips down to the bottom. Remember, a can't be 0, because if a is 0, you actually get a linear relation, because the quadratic term disappears. It's just a straight line. So let's put a back to around 1. There we go. Now let's vary the b value. And actually, in all of those, I should have been saying here, two intercepts, because 2x intercepts, because the b value is positive. Remember, if I change this, b value is positive, b value is positive. Even when I went over here and the a was negative, now I've changed it so see the vertex is here and opens down. So the discriminant value is negative, no real roots. And you see this is undefined. These are the two quadratic values giving you the two roots. See, my roots are at 3, that's that one, and about -1, that one there. Those are my roots. So these two quadratic formulas give me the two roots. This is the discriminant value that would be underneath the root here. So let's do the b here. I've got b at -2 right now. When I change b, what it's kind of doing is rolling on that intercept. See, the intercept is actually, that's the y-intercept right there. It's -3. Changing the b value doesn't change at all, but it kind of rolls around that intercept. And so I can't actually make it go from like 2 roots to no roots using the b value here at all, because it's not moving it up or down like off the y-axis at all. So all of these discriminant values are positive because we have 2 different roots. Okay, so let's put it back to around 2. Okay, so the c value, right now the c value is -3. And okay, so it's about -2 there. So notice it switched, went from -3 to -2. Let's go to -1. Oh, it's -1. Pretty close to -1 right there. Okay, it's 0 there, so the y-intercept is, well, pretty close to 0. Let's go up to 1. So, well, pretty close, actually. So I've got a c value here that's given. The discriminant is pretty small here, and notice that means that the two roots are actually pretty close to one another. If I make it a little bit bigger, I wish I could get this one to 2. Don't think I can. Right on 2. No, it's really close. So now if I make this just a little bit larger, okay, that's pretty close. It looks like on the graph like there's only one x-intercept. There's actually 2 different ones because those numbers aren't exactly the same. They're really close. So notice that the b squared minus 4ac value is almost 0. I can't quite actually slide and get it on 0, but you see what's happening here. Oh, that gets really close to 0. It looks like there's one root. And if I move the graph up, see, this is actually just a vertical translation. You know, if I made c about 3, that's pretty close to 3 there. Oh, right on 3. Then my discriminant value is negative now because the vertex is up here and it's opening up, so it doesn't cross the x-axis at all. And notice in those cases the roots are undefined. There are no roots because of the fact that the discriminant is a negative value. So that's just a little bit about the different values, just showing you that. Okay, back to the presentation. One example here on the next page that says determine the value of k so that f of x equals 2x squared minus kx plus 8 has no real roots, 1 real root, and 2 real roots. Okay, so we're going to all the different possibilities, and I'll explain what this number line's about in a moment here. So let's write out the a value, b value, and c value. So a would be 2, and I'm doing this down here because I'm going to put underneath the solutions here. I'm going to do the work for the discriminant down here. So a is 2, b is the negative k value, that's the coefficient of the x, and c is the 8. And so let's find the value of the discriminant. So b squared minus 4ac. So let's fill in 2 in place of a. Okay, so now k is negative k is the b value. So there's a negative k squared here. 2 is the a, so minus 4 times 2, and c is 8, so that's why there's an 8 on the end. Now if we square negative k, it means negative k times negative k, which is positive k squared. And 4 times 2 is 8, times another 8 is 64. So that's the discriminant expression. And I'm going to do the one real root first, and then I'll get into the other two. So remember on the previous page, one real root occurs when that discriminant expression is equal to 0. That's when you get one real root, when the vertex touches the x-axis. So I want to solve for k here. So we want to isolate for k, so I'll bring the 64 over and take the root. And remember, there are two roots of 64. If you don't put the plus or minus here, you might think it's only 8, but it's 8 and negative 8, because negative 8 also squared gives you 64. So if k is 8 or k is negative 8, which is this number here and this number here, then those are the only two numbers that give you exactly one real root, because in those two cases the vertex is on the x-axis, but only for negative 8 or 8. Well, now let's do the two real roots, and then we'll get into no real roots. So I want to set the discriminant expression, say it's greater than 0. So I'm going to, now the only difference here is it's greater than instead of equal. So k squared would be, when I isolate for k squared, greater than 64. What numbers do you square and get a number greater than 64? So if we look at the number line here, this is what the number line is for. So if I had a number out here like, let's say 9, for example. If I put 9 in here, see 9 squared is greater than 64, 9 squared is 81. Okay, so that's an example of a number that would be in the solution set for this. And in fact, anything bigger than 8, going in this direction up here, if you square it like 10 or 11.2 or something like that, squared is going to be bigger than 64. But also numbers below here, like for example, let's say this was negative 8.5, for example, 0.5. It's a little bit below negative 8. If I take my calculator over here, bring it over here. If I take negative 8.5, for example, and square it, notice you get a number bigger than 64. So any number below negative 8 is going to be in the solution set here. So anything down here is going to be a number, when you square it, you get bigger than 64. So the solution set here is actually k is either less than negative 8, any number less than negative 8, or greater than positive 8 will be a solution for this. Any number that's below negative 8 in here is going to give you two real roots or bigger than positive 8. Notice that I don't have an equal sign here. The equal gives you exactly one real root because it makes that discriminant 0. So numbers between here and here, if you square them, you will get something smaller than 64. And that's what we want over here, the discriminant to be less than 64. So, for example, if I take a random number in between here, let's say 2, for example. See, 2 squared is much smaller than 64. In fact, even if you get up here close to 8, like 7.9, for example, if you square that, it's still a little bit less than 64. And even if you were way down here, like, if you had like negative, 6.82 or something like that, it's getting close to, a little above negative 8, and you square that, see, it's still smaller than 64. So numbers between negative 8 and 8, any of those, when you square them, it's going to be give you a value smaller than 64. So the no real roots occurs for values of k between negative 8 and 8. So between here, no real roots. At negative 8 and 8, one real root, and then below negative 8 or above 8 is where you get the two roots. So that's how you can use the discriminant to figure out how many roots there are, by looking at the value of the discriminant, whether it's 0, whether it's positive, or whether it's negative. And that's the end of the tutorial.